A rectangular tank that is 108 feet cubed with a square base and open top is to be constructed from a sheet of steel of given thickness. And we're asked here to find the dimensions of the tank that require the least amount of material to build. To get us started here, I'm going to sketch a picture. So here is our rectangular tank, and this tank has a square base. So here we go. So we have a rectangular tank here with a square base. So we know that these two sides at the bottom are equivalent. We'll label them as x. And we can say that this here, our height, can be y. And we also want to make a little love note here to ourselves that this top is open. So it doesn't have a side there. Now, in this question, we're given that this tank holds 108 feet cubed. So we are given a volume of 108 feet cubed. And since this is a rectangle, we can even further say we know that the volume is the length times the width times the height. So x times y is 108. And so we've attained our constraint equation. We have x squared multiplied by y is 108. And so this is what is restricting us here, our constraint equation. Now the goal of this question is to find the dimensions. So we want to find x and y. So we have x is equal to what and y is equal to what? That require the least amount of material to build. So we can say such that the surface area is minimized. And we know that it's the surface area because those will be the sides that make up our box here. So the surface area, right, is going to be the sum of the area of all the side faces. So we need to define the surface area equation. And I'm going to define our surface area here as S. So we want to define the equation for surface area. And so looking at our sketch here, we can see that, again, we have that square base. So the area of this square base down here is going to be x times x. So we have that this is x squared plus, now if we're looking at the front, so actually if we look at any of the other sides, because we have this square base here, every rectangular side has an area defined by x times y. And we can see in looking at this, we have one in the front, we have another here on the side. We also have an area in the back that we need to consider, as well as on our left-hand side. So we have 4 side areas here. So this is going to be plus 4 times the area x times y. And then, of course, we want to keep in mind that this top is open, so we'll leave that as it is. So we have our objective equation. And so we can now use our constraint here to rewrite the objective in terms of one variable. So we are going to rewrite the surface area. Again, we are rewriting the surface area with our constraint. So our constraint was x squared y is equal to 108. And since we have y all by itself here, I'll divide both sides of the equation by x squared, which leave us with y is equal to 108 all divided by x squared. And so we're now ready to replace the y in our surface area equation with the y of the constraint equation. So our surface area now becomes S is equal to x squared plus 4 times x, and now I'm replacing that y with 108 divided by x squared. And we can simplify. We see that this x will cancel with one of the x's in our denominator, leaving us with x squared plus 432 divided by x. So our surface area equation, again, I'm just going to rewrite this because we know we want to differentiate. So this is x squared plus 432 times x to the negative 1. And we're ready to find the critical values. So we are now going to go ahead and set the derivative of surface area equal to 0 and solve for x. So we have 2x minus 432 times x to the minus 2. And so let's think we can factor out a 2 here. So this is 2 multiplied by minus 216 all divided by x squared. So if we set this equal to 0, we can now divide both sides by 2, which will leave us with x minus 216 all over x squared set equal to 0. And to find those critical values, we need a common denominator. So we can think about x as being x over 1, and we'll multiply the numerator and denominator here by x squared, which gives us, actually we'll start up here, we have enough room. We could say that this is x cubed minus 216 all divided by x squared is equal to 0. And to remove those fractions, we can now multiply both sides of the equation here by x squared. So the x's cancel each other out, and we're left with x cubed minus 216 is equal to 0. And so now it's safe to solve for x. We have x cubed is equal to 216. So we can take the cube root of both sides of the equation, which leave us with x is equal to 6 centimeters. And so now we can use this minimizing x value to find y, or to find that y dimension that minimizes our surface area. So again, recall from the constraint equation that y was equal to, or we defined y as 108 all over x squared. So we can now substitute 6 in for x. And so we have y is equal to 108 all over 6 squared, which is 108 over 36, which leaves us with 3. And so these are the dimensions that minimize the surface area, or require the least amount of material to build.